Hi, this is Dr. Ken Clark, and this is ALTIS, Need for Speed, Sprint Biomechanics, Acceleration, Module number 2. If you have any questions as you are watching this module, please feel free to contact me at the Westchester University Human Performance Lab or to reach out to me on social media at Ken Clark Speed. The ALTIS, Need for Speed, has 5 acceleration modules. This is the second of those modules, force application during acceleration. An overview of acceleration module 2. First, we will review Newton's laws. Then we'll take Newton's laws and apply them to sprinting. Then we will look at force application throughout acceleration. So a brief review of Newton's laws of motion. First law, inertia. Second law, force equals mass times acceleration. Third law, action-reaction. And we'll briefly cover these in more depth on the next few slides. So Newton's law is number 1, inertia, states that an object at rest will remain at rest, and an object in motion will remain in a constant state of motion unless acted upon by an unbalanced external force. Law number 2, force equals mass times acceleration. The units of this for force are, of course, newtons, mass in kilograms, and acceleration, change in velocity divided by change in time. So how can acceleration be described? Quite simply, rate of change of velocity. Change in velocity divided by change in time. Now, we can divide both sides of this equation by mass, and the result is that force divided by mass is equivalent to acceleration. The practical applications of this are that more massive objects require more force to cause an acceleration. As it relates to running, mass-specific force is crucial for sprinting performance, both in the acceleration and top speed phases. Rule number 3 is action-reaction. For every action, there's an equal and opposite reaction. During sprinting, there's an applied force. In acceleration phase, this is down and back into the ground. And then there is a ground reaction force, often abbreviated GRF, that is equal in magnitude and opposite in direction to the applied force. If we examine forces during initial acceleration, and we're looking mostly in the sagittal plane, we will see a total ground reaction force, and this can be decomposed for the sake of analysis into the vertical force component and the horizontal force component. The runner's goals during initial acceleration are number 1, to apply enough vertical force to support and lift the body, and number 2, to direct the rest of the force horizontally so that the action-reaction forces can propel the runner forward. If we look at Newton's laws in a testing situation such as the NFL Combine, the relationship between force, mass, and acceleration as presented in Newton's second law provides good insight as to the general relationship between broad jump test scores in the NFL Combine and initial acceleration as represented by 10 and 20-yard dash times. And it really just boils down to the ability to apply large amounts of mass-specific force at optimal angles. In a heterogeneous population, such as at the NFL Combine, we'll see a pretty strong general relationship between broad jump scores and 10 and 20-yard dash times. If we look at forces during initial acceleration a little bit more specifically, we'll note that mediolateral and rotational movements naturally occur as we watch the posterior filmed video of these elite sprinters on the left-hand side. And again, take note of all of the side-to-side and rotational movement that is naturally occurring. However, while research is emerging on this aspect of sprint biomechanics, it's not comprehensive yet. And for the purposes of simplicity, this acceleration module will focus on vertical and horizontal force application during initial acceleration. If we look at horizontal forces during initial acceleration, we can see that when the foot strikes the ground during initial acceleration, this is typically in steps 3 and beyond, and the center of mass is behind the foot at initial touchdown, there is a braking force that's applied to the center of mass, which slows the body down initially. When the center of mass translates in front of the foot, there's a propulsive force, which accelerates the center of mass during the latter portion of ground contact phase. Increases in velocity throughout the step in acceleration really come down to a balance between the propulsive forces and the braking forces. To have a greater increase in velocity during acceleration, need to have increased propulsive forces and decreased braking forces. And just to be clear on the precise terminology, what we're really talking about is impulse, the area under the force-time curve. The goal is to increase propulsive impulses and decrease braking impulses. This is obviously just a schematic of the ground reaction forces, as a real graph looks something more like this from Hunter et al. As the sprint progresses and the body becomes more upright, the braking forces increase and the propulsive forces decrease. This is related to the body posture and where the foot strikes relative to the center of mass. So in initial acceleration, when the center of mass strikes in front of the foot or just slightly behind it, there'll be a very small braking force and a very large propulsive force, as we can see in this diagram on the left. As the athlete continues with acceleration and the foot lands further out in front of the center of mass, the braking force increases and the propulsive force decreases. If we also look at vertical forces during the course of initial acceleration, it's important to know that vertical impulse during each step has to support body weight to keep the runner upright and transitioning to an upright body posture. And again, impulse is force times time, or the area under the force-time curve. So vertical impulse is equivalent to the average vertical force applied during the ground contact times the ground contact time. Now we know from our last module that as running speed increases, ground contact time decreases. That means to apply the necessary vertical impulse with each step to support body weight, that as speed increases and ground contact time decreases with each step, the average vertical force has to increase with each step to accomplish the necessary vertical impulse to support the body. What that means as it relates to the body posture and ground reaction force vector is that during acceleration, the vertical force will be relatively lower in the initial steps, and as the body posture becomes more upright and the ground contact times get shorter, the vertical forces will increase. It also means that vertical forces from step to step will look something like this, and the ground reaction force vector will become progressively more upright. If we looked at synchronized video from the Westchester University Human Performance Lab of both vertical and horizontal forces during a block start, what we can see is that if we look at the vertical forces in blue and the horizontal forces in red, there is a period of 2-foot push-off and then 1-foot push-off. And then there's a period where no force is applied to the ground while the runner is in the air briefly. And then when the runner hits the ground for step 1, we can see a secondary trace. What's interesting, if we look at just the forces from the very first block clearance step, what we see is that the vertical and the horizontal forces are essentially equivalent. In other words, the forces that are applied to project the runner's center of mass out at a 45-degree angle approximately requires balanced levels of vertical and horizontal forces. Again, the goals of initial acceleration, whether it's from a track start, 4-point block start, or from an upright or a 2-point moving start, are number 1, to apply enough vertical force to support and lift the body, and number 2, to direct the rest of the force horizontally so that the action-reaction forces propel the body forward. as the body becomes more upright, the net force vector becomes more vertical. In this video, the athlete is transitioning upright as he proceeds through initial acceleration. We see the vertical force in blue and the horizontal force in red. What we notice is, compared to the last slide where the athlete was starting out from a stationary start, as the athlete transitions upright here, the vertical force is larger in magnitude and the horizontal force is becoming smaller in magnitude. This video is nicely backed up by recent evidence from Shachi et al. And what we see here in their data is in the panel A on the left, we have vertical forces, and in panel B on the right, we have horizontal forces. They examined acceleration both initially and then as athletes transition throughout acceleration. And what we can see is in high acceleration ground contacts, i.e. ground contacts where the athletes really increased their velocity a lot with each step, those are in blue. Those are characterized by relatively lower vertical ground reaction forces in panel A and relatively greater horizontal propulsive forces in panel B. In contrast, in the medium and lower acceleration steps, as the athletes transitioned upright, we can see that the vertical forces became greater, characterized by the red and the green trace in panel A, and the propulsive forces became less. The net propulsive forces became less, as characterized by the red and green traces in panel B. In other words, higher accelerations had less vertical force and greater horizontal propulsive force. We can examine forces from acceleration from the beginning of a sprint all the way to upright sprinting through some great recent research, both from Rabita et al. And also from Ryu Nagahara's group. And here we can see vertical, anterior-posterior, which is horizontal, and medial-lateral, which is side-to-side forces, all the way from block clearance, or step 0, all the way up through step 28 of a sprint. And this is essentially from a start all the way through top speed. And what we can see is, if we focus on the vertical and horizontal, i.e. anterior-posterior forces, is that the vertical forces gradually increase with every step as speed increases and contact time decreases. And the anterior-posterior forces, or the horizontal forces, start out as nearly entirely propulsive in nature, i.e. with very little braking period. And that as the athlete increases in speed, the braking forces start to increase and the propulsive forces start to decrease. This is nicely illustrated by this video, and here if we watch in the upper left-hand corner, what we can see is that as the athlete transitions from the start to upright sprinting, the vertical forces, which here are portrayed in red, gradually increase with step to step. The horizontal or anterior-posterior forces, which here in this video are illustrated in blue, again gradually demonstrate greater braking forces at the beginning of ground contact and decreased propulsive forces in the latter portion of ground contact as the runner increases in speed. Again, here in initial acceleration, relatively lower vertical forces, minimal braking forces, and larger propulsive forces. And then as the athlete transitions into upright mechanics, we see the vertical forces get larger in magnitude, as do the braking forces at the beginning of the ground contact phase, and the propulsive forces in the latter portion of the ground contact phase get smaller in magnitude. If you're interested in reading more, here are the references that were used for background information for this module. And again, if you have any questions, please feel free to contact me.